Jordan, before we begin, I must ask you about the moon.
We're starting there already?
At the end of our last conversation, you said that humans have traveled to it and returned. Such a statement is not easily dismissed.
Fair. Okay, the short version. In 1969, 3 astronauts rode a giant rocket into space, orbited the moon, landed a small craft on its surface, walked around, planted a flag, collected rocks, and then flew back to Earth.
Using the same gravity and the same laws of motion we discussed?
Exactly. Your ideas were in the mathematics behind the rockets, their trajectories, and the don't crash into the moon part. All of it.
I write a few laws, step away for a few centuries, and people begin leaving the planet. An unexpected sequel.
And that's why today's episode matters. If your 3 laws of motion helped launch humans to the moon, we should probably understand what they actually say.
Agreed. Let us trouble your audience with some very useful rules.
So, for anyone just joining us, what exactly are these laws of motion you're so famous for?
They are 3 simple rules describing how objects behave when forces act upon them, or do not.
3 rules that somehow explain cars, footballs, rockets, coffee cups, and people falling upstairs?
If they possess mass, they are implicated.
Perfect. Let's begin with law number 1. What does the first law say in non-textbook language?
Things are remarkably content to continue doing exactly what they are already doing. If an object is at rest, it prefers to remain at rest. If it is moving steadily, it prefers to continue moving steadily. Only an external force persuades it otherwise.
So objects are stubborn.
Extremely. We call this stubbornness, inertia.
Can you give us a picture?
Consider a book upon a table. It does not flee merely because you glare at it suspiciously. It remains still until you push it. Now, consider yourself on a bus. If the bus halts abruptly, your body continues forward, briefly, with great confidence.
That moment where everyone pretends they meant to lean like that?
Yes, a public demonstration of my first law.
And when a fan keeps spinning after you turn it off?
The blades persist in motion until friction and air resistance slow them, regretfully, to rest.
So inertia is basically the universe saying change is hard.
An unusually compassionate interpretation, but correct.
All right, law number 2. What does it deal with?
It describes how much an object's motion changes when a force is applied. Greater force produces greater change. Greater mass resists that change.
Translate that for a common person. Maybe someone pushing a shopping cart.
An empty cart responds eagerly. A full cart responds with suspicion.
Same push, but the full cart is like, no.
It is not a refusal, Jordan. It is simply a request for more energy. Mass is a debt that must be paid in force.
Any other picture?
2 children on swings. Push them equally. The lighter child swings higher. The heavier child does not, unless you exert more force. Nature is democratic in principle, but not in outcome.
So, big change needs big push, especially if the thing is heavy.
You have spared your audience several equations.
Now, the famous one. The 3rd law. Every action has an equal and opposite reaction. What does that actually mean?
Whenever one object exerts a force, another force of equal strength pushes back in the opposite direction. This occurs whether you notice it or not.
So if I push on a wall,
The wall pushes on you. You feel this as a steady pressure on your hand. If the wall did not push back with equal vigor, you would not be leaning against it. You would be falling through it.
but the wall is a rigid material, right? How is it pushing back like that?
It only looks perfectly rigid. Its atoms actually squash a tiny bit, like a very stiff spring trying to spring back. That elastic shove is the wall's push on you. And if you do not have enough friction with the ground, that same push can even make you stumble backward.
And when I sit on a chair,
You push down. The chair pushes up. If it did not, you would be on the floor.
all right, let's talk about rockets, because this is where your third law really shows up.
With pleasure. When a rocket burns fuel, it forces hot gases downward. Those gases push back, and that push sends the rocket upward with equal force. The rocket does not flee the exhaust. It is thrown by it.
So space travel is basically very controlled throwing.
An inelegant description, yet entirely correct.
And what about balloon rockets? Does the same rule apply?
Exactly the same rule applies. Air escapes one way, the balloon moves the other. Action and reaction.
Even walking follows the third law, right? Your foot pushes the ground back, and the ground pushes you forward.
Indeed, you advance through the world by repeatedly shoving the earth behind you. The earth is simply too massive to notice your insolence, so you are the one who ends up moving forward instead.
So with your three laws of motion and your idea of gravity, you could explain falling apples, orbiting planets, and even help people design rockets that reach the moon.
They provided a firm structure to what had once appeared to be chaos in motion.
But motion isn't just on or off. Speeds change every instant. Directions shift. Light bends. And to follow all of that precisely, you needed new tools.
Indeed, if the universe writes its story one moment at a time, one requires mathematics capable of keeping pace with each moment.
Which leads to your next set of ideas, splitting light into hidden colors, building a new kind of telescope, and inventing calculus, the mathematics of change itself.
A necessity, not a flourish.
From rainbows revealed in a darkened room to the invention of calculus, Sir Isaac Newton's story is far from finished. We'll continue next time.